All right, so I'll be speaking in English today, so you can improve your listening skills. My name is Max Koretskiy. I'm also known as the Wizard. I like to talk and write about some really complicated stuff, sometimes even puzzling and confusing stuff. That's how I got this name, the Wizard, mysterious. And I'm the founder of Angular in-depth community. Does anyone know here of Angular in-depth? Oh, cool, right. Yeah, because, yeah, all right. So I also work as a developer advocate for AGGrid. So I speak about this product. This is where we create the best JavaScript data grid in the world. So it's super fast, has a lot of features. If you need a data grid, definitely check it out. And today we'll be talking about what makes Angular and React so fast. So in particular, we'll talk about a few optimization techniques that these frameworks use to run JavaScript really fast. Okay? But before that, I want to tell you my story. So I've been programming a little bit more than 5 years, but I'm a big fan of 100-hour work weeks. So let me just show you how fast you can move if you put in a lot of effort. So I started programming in 2014. This is when I started a startup. Unfortunately, it failed, but it made me learn to program. So then I decided to participate in Stack Overflow. I contributed a lot to JavaScript activity and in Angular. So today I have about 50K reputation. Then I used that knowledge to start Angular in-depth. It's a blogging platform at this point. And in 2017, I started speaking. This is the logo of NG Vikings, the first conference that invited me to speak. After that, I've given talks at NGConf, Angular Connect, so across the world. And so that all helped me get a job at AGGrid. This is a London-based company, but I'm here in Ukraine. I'm working remotely. I'm traveling around the world, so this was my ultimate dream 5 years ago. So if you want to learn more, I've written an article that describes my experience, the lessons I've learned, steps I've done, people that helped me get there. You can check it out. OK, so let's start with our topic today. So what we'll talk about? We'll talk about monomorphism. Does anyone here know something about monomorphism? OK, a few people, cool. Yeah, so that technique is used in both Angular and React. We'll also talk about bit fields, or they're also called bit vectors and bitmasks. And we'll talk about Bloom filters. It's used in Angular. I'll show you where. So I want to say thanks to these people. These are the people who helped me with this talk. So these are core teams of Angular and React, and also Benedict from V8 optimization team. All right, let's start with the first one, which is monomorphism. And when I started digging deep into Angular sources, this is the comment that I found. This is by Mishka Havary, who's the technical lead of Angular. So in this comment, he says something about view nodes, right? And he says that there's only one type for all view nodes, and they do that to make property access monomorphic. To be honest, when I first saw this comment, it didn't make much sense to me, right? Because I didn't even know what is monomorphic, what is view node. So it took me a year to figure this all stuff out, and I'll show it and explain it to you today. Then I found another comment by Sebastian Markbach. This is in React sources. So different frameworks, but he talks kind of about similar concepts. He talks about some hidden class, and he says that fiber nodes, all fiber nodes, share the same hidden class. And again, I didn't know what this hidden class was back then. I didn't know what fiber node was. So, but I felt it was kind of similar to view nodes in Angular. And I'll explain to you both fiber nodes and view nodes in this talk. So yeah, so these are the questions that we'll talk about. So we'll talk what is fiber node in React and view nodes in Angular? The people who work with React, have you ever encountered the term fiber? Have you ever seen fibers? OK, very few. And in Angular, view nodes? Nope? OK, just yeah. Well, after this talk, you will be able to answer yes to these questions. OK, so also, we'll talk about what is hidden class and why is it shared by fiber and view nodes. Why is it important that fiber and view nodes have the same hidden class? OK, and we'll talk about what is monomorphic property access, right? And why it's so important that this access stays monomorphic. OK, now let's start with view nodes. So both fiber nodes and Angular nodes, or view nodes in Angular, this is a data structure that is used internally inside the framework to describe the elements that need to be created in DOM. OK, so here's the simple component. It's a definition of Angular component. And we have a template with two elements, right, two headers. So this is what we as developers define. But then there is DOM, right, that browsers use to render visual representation. And in between, there are view nodes. So Angular creates two view nodes, each view node describing a template in, describing an element in the template. These view nodes, they describe metadata. So basically, they say what kind of DOM elements need to be created. So in our case, this will be two headers. And they also have or describe some metadata. Like, for example, in Angular, we have bindings that define which part of a template needs to be updated during change detection. OK, so these view nodes, this is internal data structures that Angular creates. And usually, we as developers don't see them. But they use it to render the DOM. OK, so same thing in React. We have the same component with the same template. And React will create two fiber nodes. Exactly the same purpose. It will describe what kind of elements needs to be created in the DOM. And in Angular, we have bindings. We don't have that in React. We have something called props. And this is what React updates during change detection. In React, this process is called reconciliation. OK, so now we know what is fiber node and what is view node. But what is common between them? Right? Why are we talking about them together? Well, the thing is, these data structures used a lot when both frameworks process changes. So imagine that we have a tree of components, and for each component, for each element inside a component, React and Angular creates these data structures. So we have a lot of these data structures. But then we also have functions that run during change detection, or when both frameworks process changes. And those data structures are passed from one function to the other, from one function to the other. And we have lots of these functions. And this is a prototype for such function. So there's a function, say, update node, right? And it takes in either a fiber node in React or view node in Angular as a first parameter. And then it reads some property on that node. And just conservatively, the properties on these fiber and view nodes are accessed over 10,000 times. So you can imagine that 10,000 times the properties being accessed during every single change detection cycle. And you have many of these. You can have several change detection cycles in one VM turn, say in 1 second. So lots of property accesses. And the problem is, inside the V8, like the virtual machine that executes JavaScript, the property access is a very complicated operation. It is very difficult and involves a lot of steps for a virtual machine to figure out where exactly in memory the value for the particular property is located. So 10,000 times, multiple change detection cycles per second, and for each property access, it needs to figure out where exactly the value is located, right? Now, I want to explain to you why it is a complicated process. You may not be the guy or the girl who works with memory a lot, so I'll just demonstrate you the high-level concepts. And we need to talk about hidden classes, or shapes, or maps. So these are all notions that describe something that virtual machines use to describe the layout of JavaScript objects. And by the way, this is the hidden class we'll be talking about now that Sebastian from React mentioned in his comment. So now you will learn what is this hidden class. And we have JavaScript objects, we work with them every day, right? But we don't see how they are presented internally inside the virtual machine. And all virtual machines, V8 and others, represent or describe the layout of objects using something called shapes. So what does shape describe? It specifies what properties exist on an object, and it also defines something called an offset. I'll show you on the next slide how this offset is used to figure out where exactly the value of a property is located in memory. But it also describes some metadata, right? Like property descriptor information, writable, enumerable, configurable. And we have these shapes that describe every single object, every single JavaScript object that you work with in JavaScript. So let me show you how the offset is used. So suppose you have one object with two properties, and then you have memory. Right? Memory is a simple array of bits. And you have an object pointer. So basically, this is the pointer to where all the values for a particular object are located. So where should we start locating these values? And you have offsets. And suppose these offsets are specified in bytes. So offset 0 means that we should start retrieving value from the start, from the object pointer. So here you can see that in binary, this is number 5, right? This is the value for the property x. And offset 1, it just means that we need to step away 8 bits from the object pointer and start locating the next value. So this is how offset is used. OK, let's get back to the shapes and answer the question, why do we need shapes, right? It's logical. When I first encountered that description, I thought, OK, I have JavaScript object and I have properties. Why do you need to create a separate data structure, right, to define the properties? I would rather put all that information that we have on shapes inside the object, right? We have JavaScript object. Why not describe exactly in memory where this property is located? And the answer to that question is we need that because we can optimize memory because of that. So let me show you. So suppose you have two objects now, not one JavaScript object, but two JavaScript objects. And what happens is when they have the same shape, what we can do is we can link both of these objects to the same shape. And this same shape describes the layout only once, right? We need to allocate memory only one time to describe the layout and the offset, although we have two objects. So if we had 1 million JavaScript objects, or 10 million JavaScript objects, we would still have only one shape, And you can imagine how much memory it saves. Okay, however, this in turn introduces another problem. And the problem is, what if we add another property to an object? Right? What if we want to add property W to the object B? Right? What do we do now? Yeah, we create new shape, right? That's exactly what happens. We cannot add the W property to the original shape, right? Why? Why cannot we add it to the original shape? Yeah, correct. So, because it would mean that the object A now has W property, but it's not true. So we need to create another shape. And now if we want to create or add another property, this will create another shape. And what virtual machine does is it links one shape to the other. And this creates something called transition chains. And now imagine that we want to retrieve the value for the property A. This is the original property that is described in the original shape. So what the virtual machine should do, it should go through each property, right? And when it comes to the original shape, it can only then resolve the value. And it will start with the property. So what's important to notice is that we also, when we create new shape, we also update the link inside the JavaScript object. You can see the link moving from the top shape to the, to the last shape. And I'm showing it with dashed lines on the screen. So we have transition chains now. And that's a problem, right? Because first, we need to figure out the prototype for an object. Then, we need to find the shape for the object. And it involves a lot of steps. And these are logical steps. If you convert them to machine code, to instructions to a processor, you will have tens and tens of instructions, which is a long time. So there is a technique called inline caching. And this technique helps with a property value resolution process. Okay, let me explain you how. So every JavaScript function that you write in your code is represented internally by some type. Let's say the same type function. And every function in JavaScript has something called feedback vector. This is just an array. It is used as cache. So it caches some information about that function. And what it caches is, first it caches the shape that was used to access a property. Then it also caches the offset, so that we don't need to resolve that from the shape. And then it defines the state. We'll talk in a minute about that. So here's the example. So we call the function getX. We pass in an object. Virtual machine figures out the shape for that object, right? And the offset, where in memory we should find the value. And now it can cache that information. So we will put the shape x to this feedback vector. We will cache the offset. So why are we doing that? So next time, when this function is executed, what we need to do, we need just to check if the shape of the object is the same that the shape we cached in this feedback vector. Right? And if it's the same shape, we no longer need to go and resolve those chains, etc. We will just take the value from the cache, the offset value from the cache. And that will significantly faster, make the process faster. And also, there's something called state. So what is state? Basically, state defines how many shapes we have seen in this function. At this point, how many shapes do we have? Yeah, just one. So the state is defined as mono. And this is where the name monomorphic comes from. Monomorphic property access, we talked about it in the beginning. It means that we resolve the value for the property, and we do that for only one type of shape. Okay? So monomorphic property access, if you pass only one type of shape, or you pass only one type of object that has only one type of shape. Interfunction. So here's an example. We have 3 objects, but because they all have the same layout, same set of properties, they all share the same shape or same hidden class. And it means that inside this function, we will cache, a virtual machine will cache the result, the offset of the X property. And during the consequent calls, it will resolve the value from the cache. All right, so we have monomorphic property access. What kind of property accesses do we have besides monomorphic? Sure, we have polymorphic. Poly means many, right? And it's also important to understand, polymorphic in virtual machine terms means that a function only shows up to 4 different types of shapes. Up to 4. So here's an example. Here are the 4 objects. And they all have different shapes because they have either different order of properties, or they have extra properties, or they have different prototypes. Okay? And here you can see that I'm executing the function 4 times, and I'm passing all these 4 objects. So at this point, the property access will be defined as polymorphic. Not monomorphic, where we only have one shape, but polymorphic. And it's still okay. Where things become really bad in terms of performance is when we go beyond 4 different shapes. And this becomes megamorphic property access. Okay, so more than 4 different types of shapes. And this is what I found inside Angular sources. They ran a few experiments, and they identified that a monomorphic property access might be up to 100 times faster than megamorphic. So now remember our number, 10,000 property accesses per one change detection cycle, 10,000. And each can have a difference of 100 times. So you can imagine how fast or how slow the properties could be resolved and evaluated. So it is important for these frameworks that all property accesses for these fiber and view nodes stay what type of property access? Monomorphic, correct. They want to ensure that the access is monomorphic. And this is this slide. Okay, how do they do it? Well, we know that they create only one type, but how many times possibly could they create? Well, we have many types of nodes in our templates, right? We have HTML nodes, we have text, we have child components. In React, we have portals, and lots of different types of objects. So if, for example, we are following the object-oriented programming paradigm, what we would do, we would create separate type for each type of node in a template, right? For element, we would need one set of fields. For text, we would need the other set of fields. Component, the third one. But if we have more than 4 types of these elements, right, we would be passing these data structures to the functions. And there would be definitely more than 4 different shapes, which is not good. So what these frameworks do, they merge this all into one type, one single type, and they put all fields from these types onto this field, onto this type. And to distinguish between what kind of view data structure that is, they use some field, say tag. So the field tag will define what kind of object we're working with, okay? So if you're interested, here's what you can find in the sources. So these are complete lists of all the types of elements that you can have in Angular in React. Okay, let's move on. So this is from React. So if you go today and download React sources from GitHub and try to look up begin work function, you'll find it there. This is the function that is executed for every single fiber node in your application. And you can see the first parameter is fiber node. So here I'm showing you how the framework uses this field, tag field. It uses switch to figure out what kind of element that is. And then it branches the logic. Okay, so that's all about monomorphism. Now let's talk about bit fields a little bit. So what is bit field? How many of you here are familiar with bit fields or bit vectors? Oh, okay, cool. You probably come from lower level languages like C++. So it's used more often there. So the bit field is just an array of bits, zeros and ones. Today you can easily define a bit field in JavaScript. So if you write in console 0b and then some zeros and ones, you will get, if you write this down, you'll get 81. This is a decimal representation of a binary number. Where does frameworks use it? Well, React uses these bit fields to encode effects, or they call it side effects. So we need to talk a little bit about what is side effect in React, and then I'll show you how this framework uses bit fields. So the new architecture in React 16. So they have 2 phases, render phase and commit phase. And during the first render phase, they process all changes. So when you update the state of a component and then call setState, right, it schedules some update processing. So it goes over all these nodes, processes all updates, and the result of the phase is a tree of fiber nodes, or a tree of, I can say, DOM elements, right? And for each DOM element, React defines what kind of operations it needs to do, right? Either it needs to insert it into the DOM, delete it from the DOM, move it, or update something in the DOM. Okay, so these are side effects, basically, what kind of things we need to do. The other side effects are calling lifecycle methods, updating refs, etc. So you can imagine that for each fiber node, you can have many side effects, right? You can, for example, if you have a span element, what you can do with it? You can update text inside the span, right? Or you can move that span to the other parent, so you can have multiple side effects. So how I discovered that? So when I debug and try to understand the sources, what I do, I sit with the debugger a lot, like on weekends, evenings, and just go through each function and explore the properties of every single data structure. So I was playing with the span node. I updated text in the input, and then I expected React to update this span, right? So I was sitting with debugger, exploring this span node. This is a fiber node, simplified just to fields. And then there is this field called effect tag. Basically, here, React encodes all side effects. So what we could do, very simple case, we could use an array, right? And just put in update, remove, just like that. But it would be quite long. So they use just this field, one field. And before the render phase, it was 0. The value was 0. But then, as it went through the render phase, the value was 4. OK? What is 4? Well, 4 is decimal, but I know that it's a binary field. So if I convert it to binary, I will get 100. So here you can see that after the render phase, React marked the third bit. Okay? So it basically said, we need to do something. And to understand what is this something, well, you can go and see the effect tags descriptor. So here you can see that update is encoded with the third bit. And this is what I expected, right? I expected the React to update text on the span node. OK. So how do you work with bit fields? Well, you define them first, of course. But then you use bitwise operators, or and and, to write down, to set some bits, or read them. So you can use or, like this, and it will set the, the third bit. Or you can use and it will read the bits. OK? Does anyone here want to work for Google? OK. Right, so there's this book called Cracking the Coding Interview. So there's, I don't know, maybe 20 pages or 50 pages that go through exercises involving these bit fields, all these bitwise operators. So if you want to go to Google, you need to know that, because they will be asking you that. And this is written by engineers who work on frameworks inside Facebook and Google. OK. Now, once we know what effects we need to apply during the next commit phase, we can just branch and use the AND operator to read the values and figure out what kind of work we need to do. And again, this is the real function from real sources of React. If you want to look it up, do it. OK, but this is very, very simple case, like extremely simple. Just one bound bit field, just encode separate bits. What can you do which is more powerful with bit fields? You can actually encode entire objects into bit fields and represent them as a sequence of bits. So let's say we have this object. Okay? This is regular JavaScript object, the ones you see every day during your work. So what does virtual machine need to do to work with this object? It needs to allocate memory. And to represent this object, it needs to allocate memory to hold a standard JavaScript object. Then it will create shape, right? Remember, we talked about shapes. It will create a shape to describe the layout for this object. And of course, it will allocate memory to hold values. Now, the question is, can we somehow avoid all those allocations? Can we not create the shape or JavaScript objects in memory? And the answer is there is. If we have some information about what kind of values the properties can hold, we can figure out how many bits we need to represent them. So suppose we know that sort key, the value of the sort key will never be above 1 million. So we can use just 6 bits to represent any number up to 1 million. Let's say for group, the number will be 50 and less. So 6 bits is enough. And first is Boolean, so Boolean is yes or no, it's 0 or 1, just 1 bit. So if we have a bit field, a plain integer, just one integer, 4 bytes, we can use it to encode our entire object inside this 1-bit field. Right? We'll just set aside the first 20 bits for the sort key, the next 6 bits for the group, and the last bit for the first. So here we have the same object. What we do now is we simply convert a decimal to binary. And here's how an entire JavaScript object is represented in binary. Right? If you then take the first 20 bits, you will be able to resolve the value for the property sort key, and so on. So, of course, people usually prefer to work with hexadecimal, so this is how it will be represented in this number system. Okay, I think, is it what you're all thinking about now? I would just rather work with JavaScript objects. Why would I need to do this hack stuff, you know? Well, it makes sense. It's a good question. If you're working with 10 or say even 100 objects, but suppose you're working with 1 million objects. Your application is very high-load application. You're processing millions of objects in a loop. So what we're going to have? With regular JavaScript object, we would have millions of allocations for objects and values, literally. With a bit field, it's just one typed array. And we'll hold simply 32-bit, 1 million of 32-bit integer values. And that's it. No shapes, no JavaScript objects, nothing. You can imagine how much of garbage collection a virtual machine would need to do to clean up after all those iterations, to clean up shapes that it no longer needs, JavaScript objects that it no longer needs. It's a lot of work. With a typed array, it's 0, almost 0. We just need to clear the pointer, and that's it. And with regular JavaScript object, of course, it's larger memory usage and potentially fragmented. I actually found this word fragmented on one forum, and I thought it would be very clever to put it on this slide. Although I understand what it means that these values will be spread all over the memory. They will not go one by one. And this is what not modern processors like. And with array, they go one by one in memory. Right? So it's easier to work with them, and it's really, really faster. So this slide demonstrates the advantage of using this technique. And actually, when I was working on this presentation, I wasn't sure if I should talk about that, right? Because it's really, even to me, it seems like a bit hackish. You know? So I asked Benedict from V8 core team what he thinks about it, whether this slide makes sense, right? And he actually said, well, I very much like this idea. So for high-load applications, this makes sense to do that. So this is not, you know, something out of space that you will never see in the real world. This is used. Okay, so we talked about monomorphism, we talked about bit fields, and now we will talk about Bloom filters. Actually, before I started working with Angular, I had never before seen Bloom filters. If you prepare for an interview, for example, at Google, you will go through data structures like arrays, right, map, hash, all these data structures that are taught at computer science. But this one is different. This is a data structure that is classified as probabilistic. Let me explain to you what it means. So this data structure is designed to give you an answer to one simple question. Is an element in the set or not? Is it present in the set or not? And, well, naturally, you can have two answers, right? The first answer is no, it's not in the set. And when you get this answer, this is 100% correct. So you can trust that it's not there. But when it gives you the answer yes, it's always maybe. I don't know, it could be there or could be not. So the probability varies. And that's why it is called, this data structure is called probabilistic. Like there's a probability, a chance that the answer yes may not be correct. And when I first saw it, I thought, very, very interesting, but why would I need a data structure that doesn't give me correct answers, right? Well, the thing is, if I only need the answer no, then it makes sense to use this data structure. And if I will get the answer no most of the time, then it's a very, very efficient data structure to use. And I will show you now how Angular uses it and optimizes heavily its execution time. But first, I want to talk a little bit about how it works. It uses the concept of bit field, the concept I introduced you to the previous slides. And again, it's an array of bits. Then, what it does, you should define some logic to produce a number for a value. So say this function calculate bit number. You pass in some value, and as a result, it gives you some number. So this is something called a hashing function, right? Well, we pass in values and we get some number in return. This logic can be completely arbitrary. So I'll show you an example of such logic on the next slide. But what's important to understand is that you get this number, and this number defines what bit you need to set. Right? So if I get number 2 for John, I will set the second bit. And then, if I want to ask, do we have John in the set? What I need to do, I just need to check that bit. So I just need to take John, produce the same value for it, and see if the bit for that value is set. And so the question, is element in a set, basically translates to the question, are the following bits set or not? Okay? So here's an example. We have an array, 3 elements in array. So if I want to know if John is in this array, what do I do? In JavaScript, I can do index of, right? Just pass in John, and it will give me position, probably. But this process is linear, right? So it will go through one element to the other. It will first check the first element, then check the second element, then check the third element. And again, if you have 100 elements or even 1,000 elements, that's fine. But if you have 10 million of elements, and John is somewhere at the end, it will take a lot of time to do this check. And what if you need to do this check very often, multiple times per second? It's very, very long. But with bit filled, it's just one operation. So let's say we define this type of logic. Very basic logic. We will just take the first letter of the value of a string, and I'll do modulo 8. So I just want to get the number for a letter and then round it to be in the range from 0 to 8. And say I have 8 bits in my bit filter. So for Anna, the number is 1. Okay, so I set this bit. For John, there's going to be 2, and for Tom, this is going to be 4. Okay? And then next time, if I want to check if John is there, I will do exactly the same. Then I will apply the bitwise operator AND, and it will give me, if it will give me a result, I'll know if John is there or not. So, and what's important, it doesn't matter if it's 1 million objects in an array, 10 million objects in an array, is just one single bitwise operator. It's just one instruction for the processor. Okay, that's all good, but if it's so simple, why the answer yes is not guaranteed? Why do we have false positives? And the problem is collisions. So when we apply the same logic, we take the first letter and we try to figure out what number to use, right? John and Jane, they both have the same letter, the same first letter. And it will give us the same number, and this will create a collision. And it means that if we only have John in our array, and we write the John, and we set the second bit, and then we will check Jane, it will give us answer yes, the second bit is set, so probably Jane is there, which is not correct. Jane is not there. And this is a problem. So that's why we should always do a full check, a full search. We will try to, if we get the answer yes, then we will go through the array and try to find the value. But again, if out of 1,000 times you know that you will get the answer yes only once, and for the rest 999 cases, the answer will be no, it makes sense to use this data structure. And instead of going one by one 1,000 times, you will go one by one only once. Okay? So, but what can we do? What can we do as developers? Well, we can improve the probability of yes. Instead of using just one bit, we can use multiple bits for each value. So in our case, for example, let's say we will use not the first one, not only the first letter, but we'll use first two letters. Right? And in this case, you can see that we have no collisions, because John and Jane have different set of first two letters. All right. So it's probably so much information, but hold on with me. Yeah, just a little bit. I'll finish soon. Just want to explain to you how Angular uses these bit fills, okay? These Bloom filters. And it uses it in its dependency injection mechanism. I assume most of you are familiar with dependency injection, right? Okay. So just to refresh the concept. So we have an injector. An injector has a lot of services defined. And for each service, we can configure which dependencies need to be passed when the service is being instantiated, okay? And usually, or at least the applications that I've seen, AngularJS and Spring framework on backend, they only have one container. It's called global container per entire application. But where Angular was different, it introduced hierarchical injectors. So we know that every front-end application today, either it's React or Angular or other framework, has a hierarchy of components. So what Angular does, it creates a separate injector for each component. And then you have, naturally, a hierarchy of injectors. And what if the last component needs a widget manager service? And this widget manager service is defined at the topmost injector. So what we need to do, we need to go up and see, okay, is this service in this injector? No? Okay, I'll go up and go up until I find it. But what's important is that at every step, at every injector, it should do a full search, right? It should go through every single service defined in this injector to find out whether this service is there or not. And it's time-consuming. If you have 3 components, that's fine. If you have a lot more components, that's a problem. So what Angular does is, for every injector, it defines a Bloom filter. And in this Bloom filter, it simply encodes what services are available in the injector. And you can guess that most of the answers, most of the time, the answer will be no, it's not here. Go up. So now we're no longer asking an injector if the service is there or not. We ask him a Bloom filter. And Bloom filter, right away, one simple operation immediately gives us the answer no. So we go up, no again, so we go up, maybe. And we know if it's maybe, then we want to check it. Okay? I find this very, very interesting and genius use of Bloom filters. The Bloom filters are heavily used inside database design, because most of the hits and the records will be no, the answer no. But these guys brought this concept to front end, which is really, really cool. Okay, how does Angular implement Bloom filters? Well, just a rough idea. So Angular uses a Bloom filter that is 256 bits in length. So I draw buckets here. I wanted to put arrays, all this stuff, but then I thought it would be very complicated. So it's just a big array. You can assume like a big array of 256 bits. And then, for each service, it defines a number, and it uses a simple counter. So this counter goes 0, 1, 2, 3, 4, and up to 256. Then it's then it goes from 0 again, because it's modular of 256. So what happens is that if you have less than 256 services in an injector, which is usually the case, you don't have more than 200 services in an injector, then every single injector will get a unique number and will set a unique bit. And it means that there will be no collisions, and the answer yes will always be guaranteed. And this is also a clever technique to use it. So dependency injection system is very fast in Angular, despite its complexity. Okay, so this is the T-shirt that I usually wear at conferences, but probably not today. Yeah, so I want to say I'll be organizing the first Angular conferences in Kyiv in June, so we'll have people from Angular core team. I'll be there speaking. So if you're interested in Angular, definitely check it out. Also, I have 2 articles for you to suggest to read. The first one is on reverse engineering. So if you want to become a better developer, if you want to learn these concepts, most of the stuff that I learned, I discovered on my own just by sitting with the debugger and going through the sources. I've described how to do that in the article. The second article, I already mentioned it. It describes my path, and I don't have a computer science background. Nevertheless, I managed to, I think, become a pretty good engineer and then move on to public relations. So you can read how you can do that. You can follow me on Twitter or Facebook or my own website. Yeah, usually, most often, I'm on Twitter, so you can DM me. And finally, this picture. So this is a mountain right at the top of the clouds. So what I want to say, I always finish my talks with this. I hope that the knowledge that you've learned today and the information that you've learned has awakened your curiosity to learn more. I want you all guys to come home and to dig deep into any tool that you're using and start reading more. And all this activity will definitely make you a better software engineer. Right? And this is what my hope is. So thanks a lot for attention. Good luck.